Okay, we have a few. Okay, so my name is Aiping Chen. I'm a scientist from Los Alamos National Lab. So let's first acknowledge the workers, collaborators. The work mostly done by the previous student right now, currently in assistant professor in China. And machine learning is supervised by his advisor, Citizen. And the TPM work has been mostly done by James Ravi from MIT and Jiaming Hu, who is also in college. It's the phase field simulation. So for those who don't know our Alamos or SIM, Center for International Knowledge, SIM is a DOE funded user facility. We are located at Los Alamos. It's a 6-hour drive from here in the north New Mexico, and we're about 30 minutes from Santa Fe. And since we accept user proposals and we welcome collaboration, and you can reach out to us for any sort of resources. And particularly for my group, we have been working on same-film synthesis and calculation and do a little bit of devising. And we are actually looking for postdocs. And if you have a postdoc which who would like to do research about Alamos, they're welcome to contact me. So particularly for my group, we're working a lot on same-film synthesis, and of course we are fascinated about microstructures, and that's why we also do ourselves and collaborate with other people doing microcharacterization. In the past few years, we have been working on different kind of materials and systems, and also microstructures, including superlattice, nanocomposites, and more exotic like 3D nanocomposites. And here outlines a couple of applications. And particularly for this talk, probably I would briefly mention about the background, and also we'll focus a little bit on theoretical use in literature about how to increase the energy storage in relaxed electrics. And then I'm going to focus on why we use machine learning to search the completion around the longitudinal and tetrahedral phase boundary, particularly in this case. And I'm going to focus a little bit on synthesis and then how to use domain engineering to increase the performance for this type of relaxers. So this morning we learned, about anti-electric used for energy storage, and I don't think we need much introduction for that. In this talk, I'm going to focus on relaxed electrics for this type of applications. And it's very simple, right? To increase energy storage and efficiency, as we learned this morning, low species means high efficiency or low loss, right? That means we need a material with higher polarization and smaller, higher polarization. Like, there's the limited amount of materials you can select, lead and bismuth base have higher polarization and has been heavily studied in the literature. Once you pick the material, other things will be very simple. It's reduce the PR and increase the EV, right? They only have two parameters. So in literature, people use different type of mechanisms, or how do I say, strategies to do this. Like the doping or ion bombardment. I think LANL published one paper in 2020 on that. And of course, you can use interface engineering methods to tune or increase the vector field. And let's take a look at a few examples in this feature. There's one work published by one group from Tsinghua University. They, of course, they engineer the domains, like they can actually introduce the PNR, polarized nano regime, in the dielectric materials like steel. And by doing that, they actually can get pretty decent, I would say, pretty good results. Like the efficiency is around 80%, and energy storage density is around 110, something like that. And of course, people do simulation to demonstrate, okay, you can see, the PNR regime, this type of materials. Okay, recently I found actually, a few days ago, I found a paper talking about, also use ion bombardment to kind of changing the film property here. as brown is the blue one, and you can see it's like ferroelectric. They said once you ion bombarded, it can induce disorder and increase, the energy storage density. Of course, as you know, they have large species. That means the efficiency is very low. And I think, LANL group reported that, they use ion bombardment. They can actually increase the spectrum field at large to almost, I think this is 5, or actually here you can see almost 6 megavolts per centimeter. And later on, you will see that our field also can achieve that. We barely can go above 6 megavolts per centimeter. I think that's kind of kind of limit almost in oxide, most of oxides. Come back here. Another strategy people use is, measure these fields in the super ferroelectric regime. Of course, that in that regime, as later shows, that you have a very slim P rules. Of course, in this work, the same group in Tsinghua University reported pretty even higher response, because this time use isthmus and very tightening. Another effect is using doping to increase the spectral field. As you can see in this work, the dope zirconium, and in some of this optimized doping condition, they can reduce the leakage current a lot. And we can also take advantage of this kind of doping in our films. Of course, there's another example people reported by using interface to reduce the leakage. So here summarize what people use in literature, and of course people use the PNR. And our work here is kind of inspired by one of the paper published in 2017, and they talk about the slush polar domain model. The difference between this model and the PNR model is that in PNR we have the cubic matrix. In this one, they say you have multiple domain states with extremely small domain size and no non-polar matrix. That means no HDO, right? So inspired by this, we want to develop a system that we can. This one will use MD to kind of simulate what happens in PMNPP. We want to do experiment to see if we can grow, some films and achieve this kind of slush domain models. And if we can, then we expect that we have very good energy storage performance. So we looked at the BTO for a lot of reasons. Of course, it's less free, so that we can work on at Los Alamos without much of problems. And of course, the ferrotitanate has been well started, so that means we have a lot of database we can select, and we can for doping. And we particularly select these 5 elements to consider, and the reason is, we can see. We just select the composition around RT phase boundary. In that case, we will have no cubic matrix. That's one of the critical points to achieve or build this slush model, right? So if we talk about these 5 elements, then if we limit the composition below 30%, you will see that there will be almost about 47,000 compositions, which is very challenging to grow, right? So we collaborate with this group, and they have been working on this ferrotitanate system for a long time, and we can, using the bulk material already synthesized and node structure, and we can build machine learning models to predict the unknown compositions. And here we built a classifier using the sport vector machine model, and we use the 180 data set to train this model. And you can see here, this is the computer metrics. As you can see, the prediction is pretty good, that with the accuracy around 92%. We can use this model and predict the 47,000 compositions. And we built around, we have about 30 phase diagrams we can do, or we can select. And we select here 3 typical phase diagrams. As you can see, as we are selecting the RT phase boundary, so that this CT phase boundary, that CR phase boundary, we can ignore, so that we narrow down a field. Here, typically we selected one of them, which is have RT phase boundary here, and this is the 0 doping, and we select 4 of them with different dopings, 1%, 3%, and 5%. By using these 4 samples, we can grow film, and we see how what we can get. This is we selected 3 dopings, and we're going to grow the film. So we use calculate the position, and we'd like to optimize the growth condition. And we here shows you we optimize laser energy, also the oxygen pressure. As you can see, most of them behave like a normal ferroelectric, like the bulk compound. Actually, we measure the bulk compound, the L ferroelectrics. In one of these films, actually, in 1.5 joule per square centimeter, you will see that it behaves very slim. So we think this will be a good candidate to start with. And let's take a look at this sample here. It shows very good dielectric and ferroelectric behavior. So, and we also grow this sample with different SPO substrates, and we see that all of them shows very slim P loops. That means this growth condition is very robust. And we, of course, we measure the efficiency, and here you can see it's pretty high, about 90%. Of course, up to 2.5 megavolts per centimeter, it would drop significantly because the breakdown field is not so high. Of course, the energy storage performance is very bad, right? Because the low breakdown field. Because we're doing a lot of thin film growth, we are very interested in microstructure. As you can see here, the film is very nice. As you can see, we have very nice sharp interface between the body electrode and STL substrate, also the BTO film with the body electrode. We also did EDX mapping for those films. As you can see, there's no really segregation of these elements. That means most of the elements are uniformly distributed in the film. Of course, we did a little bit more like band gap measurements. It shows actually the dope calcium zirconium dope material actually shows very similar band gap with compared to BTO, is slightly higher. That means these films have relatively simple to BTO band gap. Then we use this kind of parameters to grow, the dope thin dope materials. And here shows the 3% thin dope STEM image. You can see that the film still shows very good quality with the sharp interface. And we did the EDX mapping, and the elements are most likely uniform distributed to confirm the film quality. So to talk about energy storage, I think we had to talk about this one, which we compared, the 4 samples we talked about before, which is the first one is without doping, without tin doping, and 1%, 3%, and 5% tin doping. As you can see, without tin doping, all of these P loops are slim, but without tin doping, this film becomes very liquid, around 3 megavolts per centimeter, right? Once you dope this sample with 3% tin, this spectral field can almost increase to 6 megavolts per centimeter. And that's, and you will see later, we actually calculate the performance for this kind of films. As you can see, this here, we have red one is 0 tin doping, and 1, 3, and 5. This red one and the yellow one is 0 and 1. As you can see, the efficiency on the right side will decrease significantly above 2 megavolts per centimeter because the sample becomes very liquid. And once we dope 3 or 5% of tin, as you can see, the efficiency can almost maintain around 80% or 88% for the 3% to always about to 5 or 6 megavolts per centimeter. Compared to BTO, this energy storage performance around 80 joule per cubic centimeter, which is pretty good, I would say, probably almost the best for the band tightening system. And of course, we use the frequency dependent measurements to confirm the relaxed behavior. You can see typical very broad transition, and with the shift of this peak, that means most likely this is a relaxation. And you will see, you might ask how this film compared to the state of the art in literature. Here, this plot is very complex. Let me break it down here. On the right side is the efficiency, is the green curve. If you compare the efficiency, I would say our field is the best. You can see it's around 90% for the 180 nanometer, and 27 nanometer is about 80%, which is higher than, I would say, the state of the art. And let's look at the green, the yellow one, which is on the left side, the energy storage density. our film is here. Of course, lower than bismuth and PCT from LANL, right? Because our polarization is lower, right? And compare, in order for a fair comparison, right? Because we have to normalize this maximum polarization, and that's why we define it for system independent people merit factor. That is the red curve here on the right side. So if you divide this anisotropic density by maximum polarization, we'll see that our film shows the maximum, shows the largest compared to the current state of the art. So I think we did pretty good job on optimizing the quality conditions and things like that. And you might imagine like what kind of microstructure or domain structure look like for this kind of system. We also collaborate with James Levy from MIT, and we get some projected polarization map for this. Left side is without tin doping, and the right side is 3% tin doping. All these both samples shows nanodomains because of this, unique Walsh condition. But with 3% of tin doping, this domain can be break down to very small size into a couple of, I would say less than 10 nanometers. So, and that will make these samples very robust and without effect from the electrofields. And of course, this is the polar plot for the polarization vector, as you can see, for the 0% compared to 3%. So the large diverse angle means you have more diverse polarization in different directions. That means, another way of saying these domains are smaller. So, and we also collaborate with Jamia Fu from University of Wisconsin, who is also in the audience, asked him to simulate what the relationship between the domain structure and domain size and with the polarization, the polarization P loop. And they find out that with reducing the domain size, or actually equivalent to doping the tin, actually we can reduce the remnant polarization. That's very similar, kind of resemble our result of doping more tin in the material actually breaks down the domains. And one final slide here is that shows you how we can use the tin or the covalent doping to actually make this sample more insulating. Here, this is all EOS measurement shows that the blue curve is SQ bound. As you can see, we have two samples. The red one is the tin dope, the green one is undoped. So as you can see, with the tin dope, these peaks are actually near to the ferroelectric SQ. That means we'll reduce the titanium 3+ valence state or oxygen vacancies in this kind of field. And with that, I'd like to summarize and take any questions you have.
Okay, we have time for a couple of questions.
I actually don't know. I looked at a lot of papers. It looks like 6 is most of the papers actually. Huh? For film. I barely see anyone who expects it. No. So 6, I think even in the first the science from Tsinghua University 6 is what they got, and you got 6, and I think we got 6 too. So it's just a magic number.
Maybe I missed it in technical way. When you're talking with students, you see uniform in terms of chemistry. And are you certainly in a position or from local or different?
Okay, that's a very good question. We actually never looked at microstructurally how tin doping is distributed because the amount is so small. we believe it's mostly, we actually ask them to look at that, but it's kind of difficult to see. But we believe it has two roles. One is reduce the leakage. The other one is really try to break down the domains. We compare the tin doping with undoped one. We do see very significant change on the domain, and the field becomes much more stable. The undoped one, to measure it, sometimes we actually can see the domain change. You measure E, suddenly it becomes kind of fat, the fat, but square, right? But this tin doped one, it never do that. So I think the doped one really makes the system much more stable.
So we don't have any more questions. Let's finish our meeting again. I guess we'll just hear about the slides.
Thanks everyone today. Great talk. Now we're talking every year.
Sorry. I know, I've been meaning to catch up.